Welcome. This is Miss Wiesen, and this is the first podcast of Unit 2. And in Unit 2, we're going to learn about molecular and ionic compounds. More specifically, we're going to focus in on their structure and properties. And so let's go ahead and label our Unit 2 notes at the top. Remember, we're keeping these units throughout the year as reference. This would also be a good time to pause me and grab a writing utensil, a physical copy of these notes, your AP reference sheet, a calculator, and of course, if you need more space to write notes, then have your notebook out as well. Let's start off with some conceptual stuff in this unit before we do a little bit more of the application component. First thing is, what is a chemical bond? And bonds are forces of attraction that basically hold groups of atoms together that act as a larger functioning unit. So bonding, the type of bond of a substance can actually tell you a lot about that substance's physical properties. A couple of physical properties that you'll hear pop up are melting point, so the ability to convert a substance from a solid to a liquid; hardness, so the if you can scratch or indent a material, or even a substance's electrical or thermal conductivity, which is basically just an ability of a substance to either resist or conduct an electrical current. So ultimately, at the end of the day, when atoms are bonding, they are going to achieve the lowest possible energy state. So we learned in the last unit that negative energy values often translate to a system that's favorable. And of course, if two elements are going to bond to form a compound, when that bond occurs, we can actually say that it's the lowest possible energy state. So if you think about it, most of the chemical substances that you know in life or can identify are not existing as actually as individual elements, but rather as compounds. And so what that means is that when multiple different element types come together to form compounds, that bonding requires less energy than the elements existing by themselves, which we also say elemental form. So one thing and a big key for this unit that will help you is that, and this is a big misconception, so let's clear it right now, is that it takes energy to break a bond, not to make a bond. In other words, energy is released when a bond is formed, and energy is required when a bond is broken. Now, over to the right, I can kind of just model that in a very simplistic way. So hopefully it's not too simplistic, but I think it will carry the message. So if I have two carbon atoms, say, for example, that are bonded to each other, and if I want to break that bond, so I'll just kind of make it look like a lightning bolt or something. If I want to break that bond, then I understand that in order to do that, I have to have energy from outside the system. It's going to be brought in and absorbed by these two bonded carbon atoms in order to break it. In other words, energy is added into the system. Now, conversely, if I have two carbon atoms that are coming in close proximity to each other and are eventually going to form a bond. So let's pretend like these two carbon atoms want to form a bond. The opposite's true, that when the bond actually forms, energy is going to be released from that system. Okay, and when you're talking about energy and energy values, we're going to always use a unit of kilojoules per mole. And you can see here how we abbreviate that, kJ/mol. So in this unit, we're going to learn about some chemical bond types. Hopefully you've heard of some of them. The first one is ionic bonds, and these form ionic compounds. They always will form between a metal and a nonmetal. And remember, metals will always form cations. An example would be calcium. It's going to go on to form a 2+, so it's going to lose 2 electrons. Okay, and then calcium will always bond with a nonmetal to form an ionic bond. So an example could be chlorine, which is a nonmetal. It's going to form a -1, and consequently, these 2 electrons that calcium release will be picked up by chlorine. You can see here, though, that this chlorine atom only needs 1 electron, so I would have to bring in another chlorine atom to take the 2 electrons of calcium, and therefore it would be CaCl2. So ionic bonds are going to form ionic compounds. These substances are going to have very high melting points. That's because the force of attraction between them is so strong. Also, their structure is very close together, and on a molecular level, they form crystals, which we'll talk about soon. The other type of bond you're going to learn about is covalent bonds, and these are always between nonmetals. Now, covalent bonds always form, we say, molecules. Okay, so when we talk about molecules and say the word molecules, we're literally talking about substances that are strictly made of nonmetals. Whereas oftentimes we'll refer to ionic compounds as compounds. So if that kind of language helps out a little bit, you might want to add that to your notes. Anyway, in covalent bonds, there's a difference in how the bond forms. They actually share their electrons. Remember, in ionic bonding, and what we just discussed, is calcium and chlorine, there's an exchange. Calcium is giving electrons to chlorine. In covalent bonds, that's not the case. They're sharing electrons. And I can do a real simple structure of two hydrogen atoms, which each have one valence electron. And what they'll do is they'll share these two electrons to form H2. And so instead of giving and taking electrons, covalent bonds is the sharing of valence electrons. There are two types of molecules that form with covalent bonds, and those are polar covalent bonds and nonpolar, and we'll discuss this in more detail soon. The third type of bond is metallic bonds. Yes, you probably haven't heard of this before, but it is basically between metals. And soon enough, we will also look in more detail on this, so stand by. Now, to understand bonds, you need to understand Coulomb's law, which we actually did cover in the first unit. And you could see that I left the equation for you here to view again. You might want to put me on pause so you can remind yourself what the variables of Coulomb's law. But if you're looking at understanding a little bit more about the force between two atoms when they form a bond, you have to understand that the values you get for calculating this will either be positive or negative. And remember, we learned that negative value numbers are oftentimes going to be favored. So if you're doing Coulomb's law and you get a negative value, it's because you're doing a calculation involving a positive cation within a negative ion and therefore an attractive force. If you're doing calculations and you get a positive number, you're indicating probably a repulsive force is occurring between two like charges. So understanding bonding, we need to review some more vocabulary here. Valence electrons, and as you know, those are the outermost electrons in the valence shell. And in chemistry, we've learned that 8 is great. So an atom is stable when its outermost shell is full. And we often call that the octet rule. That's because typically speaking, outer shells want to have a full octet or 8. There is an exception with hydrogen and helium. Remember that first shell can only hold 2 electrons. So the exception with hydrogen and helium is that they can achieve a duet. So remember, when we're talking about bonding, bonding is going to occur between the valence electrons between two atoms. All right, electronegativity. Now, we learned this trend in the last unit, and the concept here is going to come up again to help us understand bonding a little bit more. It's defined as the ability of an atom within a molecule to attract shared electrons to itself. So think of a tug of war. In just a minute, I'm going to show you that we're going to use something called the Linus-Pauling scale to help us determine the types of bonds that are going to form based on electronegativity values. The Linus-Pauling scale is going to go between a value of 0 and 4.0. And in just a second, we will see that. Now, it's important to note that differences in electronegativity between atoms are going to give rise to something called polarity. Now, I indicate here, I put this picture in your notes of a water molecule, and you can see here that the oxygen atom has an electronegativity of a 3.5, and the hydrogen atom has an electronegativity of 2.1, and these are values given by the Linus-Pauling scale that I just spoke of. Now, if you take the difference in those values between the hydrogen and oxygen bond, you're going to get a 1.4. And so that value tells us the type of bond that's going to form. And right off the bat, we don't need necessarily to do math to understand the type of bond. We can quickly see here that oxygen's a nonmetal, and so is hydrogen. So we know a covalent bond is going to form. But earlier, I spoke of a polar versus a non-polar covalent bond. And so right now, these two types of covalent bonds can be determined through electronegative values. And again, we'll look at this in just a second in a little bit more detail. Now, one more thing I'd like to say about polarity is polarity creates something called dipole moments within molecules. And if you can remember, polarity is basically a phenomena that occurs when the difference between electronegative values causes a pull of electrons towards the more electronegative atom. So in this example of water, oxygen is more electronegative and will consequently pull in electrons towards itself, making this side of the molecule slightly more positive. And so we use this lowercase lambda sign to represent partial, and we put a little minus sign. So this little s means partial. And because most of the charge is over on that side of the molecule, it consequently makes hydrogen a little bit partially positive on this side. And so because of this difference in charge on the two sides of the molecules, we call this a dipole moment. Okay, so we're going to look a little bit more and see and deal with these Linus Pauling values to determine electronegativities right now. But a quick disclaimer, and on electronegativity, before we cover in more detail, we need to remember that the trend has electronegative values in increasing order from left to right and decreasing values from top to bottom. And you have to ask yourself why that is. Well, of course, the answer lies in the atomic structure, of course. And so before we move on to understand why electronegative values increase from left to right, and that is because, remember, as we go from left to right, the radius of the atom decreases. And that's because the nucleus has quite an effect on pulling those negative electrons in with its positive charge. And so as we go from left to right, atoms are going to get smaller in size and have those electrons are going to be really close into the nucleus, causing a greater pull of negative charge. So it should come as no surprise, like elements like fluorine right here have an exceptionally small radius, and it also happens to have the highest electronegativity. So think of kind of like a magnet when you think of electronegativity. If you've ever held a magnet with opposite polarities, so one north pole and one south pole, and you can start to feel the pull as you get a little bit closer. And so you can kind of think of electronegativity like that, this attraction of an element to take on more electrons. Okay, let's take a look at the Linus Pauling ranges. And if you look at the data table at the bottom of page 2, what you would do is you would take the electronegative values of two elements and take the difference between the two of them to ultimately determine if the bond is going to be that will form is nonpolar covalent, or if it is polar covalent, or if it is ionic. Okay. And so we could use these ranges to kind of tell us the specific type of bond that forms between two elements. As an example, at the top of page 3, for example, an ionic bond, this is when you have two elements that are bound together and their electronegative difference is greater than 1.7. Let's go ahead and pop on over here to this periodic table and take a look and do an example of an ionic compound. An example would be sodium and chlorine, a metal and a nonmetal. And right now you can see their values. And so I'm going to go back over here and just write an example in my notes up here to the top. So if I show sodium bonding to chlorine, I know the values. I'm just porting them down from the table. And so the difference in electronegativity between these two is a 2.1. And so clearly this is greater than 1.7. So we would qualify this bond type as ionic. Now, a polar covalent bond is if two elements bond and the electronegative difference is between 0.4 and 1.69. Let's go over here to the periodic table. And I always like to use water as an example of a highly electronegative molecule. Hydrogen's over here and oxygen's over here. I just circled them. Looking at those values, let's go back to our notes and kind of write the example in our notes. So the bond that forms between a hydrogen and an oxygen within a water molecule Well, I know, and this was in the example in the notes above, but hydrogen has a value, an electronegative value of a 2.1. Oxygen has a value of a 3.5. And the difference between these two would be a 1.4. And if you go back and look at our ranges that are listed here, between a 0.4 and a 1.69, that would be qualified as a polar covalent bond. And then lastly, a nonpolar covalent bond would be two elements that have a difference of electronegativity that's less than 0.39. And a good example could be dihydrogen sulfide. So let's go ahead and take a look at hydrogen and sulfur. You can see their electronegative values here on the table. And let's go back, put this example in our notes. And so the bond between a hydrogen and sulfur would consequently have electronegative difference less than 0.39. And you can see here, hydrogen's got 2.1, sulfur is 1.8, and the difference between these two would be a 0.3. So that's how you're going to use the Linus-Pauling scale. You don't need to remember all the specific values on the periodic table. You just need to recognize when there are two elements bonding, and according to their electronegative values, what then would the bond type be? All right, let's do a little bit more exposure with some of these practice problems. It's asking in exercise 1, why is fluorine the most electronegative element? And it wants us to explain this in terms of effective nuclear charge or in terms of Coulomb's law. So back over at the periodic table here, let's go ahead and take a look. We know that as we go from left to right, that it steadily becomes more electronegative, but also the effective nuclear charge increases as well. And so you can see where fluorine is at. It's the most highly electronegative element, and it's in the second period. Now, fluorine, which has an atomic number of 9, means that it has 9 protons. And if it's neutral, it's going to have 9 electrons. So if I quickly drew a model of fluorine, you can see that it has 7 valence electrons that are attracted to the 9 positive protons inside the nucleus. And so that effective nuclear charge is really strong because the atom is not very big, and those opposite charges are really bound tight to each other, holding that atom in really tightly, causing that positive nucleus to want to draw in more negative charge. Now, for Coulomb's law, we know that the charge and the distance are two things we need to consider. And as we go from left to right, the distance between the positive charges and the negative charges of an atom, it's a relatively short distance, and the charge is relatively high. And when you have that, you're going to have a very, very strong force of attraction between the atoms. Again, this is going to cause the fluorine to draw in more negative charge. So I'm going to go ahead and just jot something down here, pause me, come back, and port this over to your notes as well. Okay, so what I just said with my words, I essentially put down for exercise 1. Feel free to copy this down in your notes or word it in any way that you see fit. Let's go to exercise number 2. Why does francium have the least electronegative element, or why is it the least electronegative element on the PT? And explain in terms of effective nuclear charge or in terms of Coulomb's law. And if you go back here really quick, we see francium's right here. Now, one thing about francium is it is huge. It's in the 7th period. It's all the way down at the bottom of the periodic table. It has 87 protons. And because it's in the first group, so it's in the first column, it's only going to have 1 valence electron. And so that effective nuclear charge is going to be super weak, because an atom that big, the atom itself is not going to be bound very tightly. And so that 1 valence electron is far away from the positive nucleus. And so that atom is not going to have a desire to pick up or take a negative charge. Remember, there's also something called shielding happening. That 1 outer valence electron in francium is being shielded by all those core electrons, making it harder to have a connection to that inner nucleus. Again, I'm going to kind of put that into words. Pause me, come back. You can write your own response. There is the response that I put for exercise 2. And let's do exercise 3. It says, order the following bonds according to polarity from least polar to most polar. So on AP examples, be sure you're reading the question carefully and responding correctly. So what I mean by that is it's asking for you to list the bonding pairs from least to most polar. So you're going to use the Linus Pauling scale. And I don't have it indicated here, but you can actually scroll back up and look at the values. But what we're looking at is a bond between two hydrogen atoms, bond between an oxygen and a hydrogen, a chlorine and a hydrogen, a sulfur and a hydrogen, and a fluorine and a hydrogen. Now, to save you the headache, I'm going to go ahead and pause my video and port down the values for each of these substances according to the periodic table above. Okay, so I pulled these values down for each of the elements on the periodic table, and if we take the difference between them, you'll see that a hydrogen single bonded to a hydrogen is 0. And let me just list the rest of them. All right, so after doing some basic subtraction, I found the electronegative differences between these. And clearly, I can go ahead and rank them now. So the answer, instead of rewriting them, I will just draw your attention here. Okay, so we're going to finish this last page here, and then we will be done with this first podcast. And what we're going to learn about in this particular part of our notes is we need to understand how chemical bonds form. And it's going to be really important to conceptualize something that you can't see. Welcome to chemistry. I mean, things are happening all the time, but we can't see them because they're occurring at the molecular level, and that is far too small for the human eye to see. So right now, we're going to outline a couple of really important concepts in bonding that will help give you a strong foundation for this unit. And we're going to start off by looking at this potential energy diagram here to the right. Now, this is a potential energy diagram of a simple covalently bonded molecule between two hydrogen atoms. Think of this as going from left to right, kind of reading this graph from left to right as I explain it. Now, what you're going to have here in this area that I just circled is you're going to have two hydrogen atoms beginning to approach one another. And as they approach one another, remember that the electrons of one hydrogen atom are going to be attracted to the positive nucleus of the other hydrogen atom. Conversely, the electrons of one hydrogen atom are going to repel the electrons from the other hydrogen atom. So this is happening to both of the hydrogen atoms simultaneously. And so when those attractive forces of each atom, each hydrogen atom, offset the repulsive forces, we're going to have a big decrease in energy, and that's when the bond forms. So take a look at your x-axis and y-axis. Your x-axis is energy, and when we go down, our energy values are decreasing. And so another way to think about this is as two atoms approach one another, the energy is going to decrease and become more negative as their electron clouds begin to overlap with each other, which, don't forget, that means that the molecule is becoming more stable. It is favored. And so you get this dip that you see in the graph of potential energy. Now, one thing that I like to call the lowest portion of the dip, if you will, is the sweet spot. Okay. And if you look here, there's two things that you can glean or get from potential energy bonding diagrams. You can actually learn the bond energy and the bond length of two covalently bonded atoms. And so I basically overviewed and said that in a series of bullet points over here to the left part of the diagram. So take a second, pause me, and see if you can see the steps that I'm putting that kind of relate to what's going on in the diagram. Bond length is defined as the distance between two nuclei where the energy is minimum. So if you look at the example up here, the distance between those two bonded nuclei is called its bond length. And so exercise 4 gives us a good example of this. And you can, again, use potential energy diagrams to determine bond energy and bond length. Exercise 4 is saying, what is the bond length, which we also call internuclear distance, All right, bond length and internuclear distance mean the same thing between the two nuclei below. One of the things I'm going to instantly look at is the dip, or the portion of the graph that has the lowest potential energy. And I'm going to kind of just draw let me do it in red. I'm just going to kind of just draw a line to indicate where my energy value would be. And I will also take that part, because if this is the part where the bonding actually occurs, then you would go straight down from there to say that would be consequently the distance between those two bonded atoms. So we answered the question. What is the bond length? It's about 75 piconanometers, or picometers rather, I'm sorry. So at about negative 450 kilojoules per mole, the bond forms with a bond length of approximately 75 picometers. Okay, so that's going to end this portion of Unit 2 notes right now. We're going to come back and we're going to come back and in Podcast 2, we're going to look into the specifics of ionic bonding. Thank you so much for watching, you guys.